Okay, this is a quick video about magnification. I'll show you what an image looks like with the unaided eye, how a magnifying glass helps, microscope, telescope. I'm going to have the algebra up here, but I don't want to talk about the algebra a lot. I want to keep the video short and just give you the idea that lots of times in textbooks, it seems like these are two different techniques or ways. It's the same analysis. You have two lenses. Both those lenses are a magnifying glass. And so it all ends up working the exact same way. I want to show you that it's really just one idea to know. Things you should know before watching this video are the thin lens equation and magnification. If you haven't gotten to the point where you've looked at either of these, I don't think this video is going to make much sense to you. So you should go back and take a look at that. But assuming you're like, yeah, I get what to do with one lens, I want to know how do I do the telescope and microscope. Hopefully this video will help with that. Okay. So the first thing to understand is how your eye sees an image. If you have some object, the thing to understand is that the object shines light in all directions. It doesn't really care about your eye. So what we're going to do is we're just going to focus on the light that accidentally makes it through your pupil. And so there's some spread of light that makes it through your pupil. You see how the light spreads out. And what does your eye do for a living? It collapses it all back to a single point. That's how you know you get a sharp image, because it all goes to one point. If you notice in this case, our image is upside down. That's not an accident. In real life, the image on your retina is upside down, and your brain, free of charge, flips it right side up for you. So you can thank your brain for that. Okay. So one way to look at how big an image is to say, what angle does it make when you enter the eye? And so in this case, it's theta 1. If I bring the object closer, I have some different angle. And notice that by bringing it closer, I've actually made the angle bigger. I'll put them side by side so that you can see that. So right now, you can see that the red object makes a bigger angle than the purple object. And if you want to know what their images look like on the retina, it's clear the red object is bigger. It's bigger, you can see more detail in it. Okay, so holding an object closer, that's the first way to magnify something. If you want something to be clearer and sharper, bigger, see the details better, bring it closer. So you might say, great, I want to see the atoms in something. Let me just bring it so close to my eye that it makes such a big image that I can see the atoms. This is a great idea, except your eye does not have the power to bend the light enough to make a sharp image. The rays are still diverging down here, and it will look blurry. It turns out that the closest that you can hold something to your eye so that it can still make a sharp image is called the near point. Here's a quick experiment you can do. Take some text, a book, anything you like, hold it at a comfortable reading distance from your face. Slowly bring the book closer, closer, closer. Eventually, the text will get blurry. You won't be able to read it. That's your near point. For most people, it's 25 centimeters. That's about what it is for me. It's probably what it is for you as well. Okay, so the biggest you can make an image with your unaided eye is to bring it as close as possible, and that occurs at the near point. Okay? If you wanted to bring something closer than the near point, you're in trouble. But of course, this whole video is about not having an unaided eye. So what do? You pop a lens in front of it. The lens bends the light a little bit. It gives your eye a head start. And now your eye has enough power left over in order to make a nice sharp image. Let's get more specific than that, though. Like, we want to know, well, what kind of lens? Where do you put the lens? Okay, so here's a lens. You know that a lens has a couple of focal points. Okay, and let's say you put an object in front of the lens. So if you do your ray tracing and you use your thin lens formula, you know that you end up with a real image on the opposite side. Okay, so by real image, we mean that if you put a movie screen there, you're going to see something. Okay, what happens when you move the object closer? Well, you get a real image that's bigger and located somewhere else. Okay, what happens if you bring it inside the focal length? No more image. You can see that the light doesn't converge anymore. In some sense, you've gone beyond the near point of this lens. Although don't say that, people will just look at you like you're crazy. You're inside the focal point. What you can say, though, is that it's not that there's no image formed. There absolutely is an image formed. It's just a virtual image. The virtual image is formed on the wrong side of the lens, and it's the result of some human standing over here, seeing diverging light, and saying, oh my gosh, I'm so smart. I know where this comes from. This comes from an object located behind the lens. And notice where you think it is not where it actually is. So maybe your brain's not so smart after all. I mean, this is helpful, but you're still a little bit wrong. Okay, this is called a magnifying lens. This is actually what a magnifying lens does. It allows you to hold an object closer than your near point to create a larger object that your brain thinks is at the near point. So look, you started with a small object. You ended up with a big image that is at your near point, so it's in focus. So in the mathematical tools of thin lenses, and we want to talk about distances and stuff, this is what the magnifying lens does. You must hold the magnifying lens close to the object so that it's inside the focal length, and then the best you can do is to see a new virtual image at your near point. The other thing you can do is, if you want, this is called relaxed viewing, you can bring the object closer to the focal point, and then of course that will move the object farther away. And when you move the object farther away, the image gets bigger. Of course, that's not particularly important to your eye. What we wanted to talk about was the angle. And believe it or not, when you move the image farther away, even though the image gets larger, the angle actually gets smaller. So it's actually to your advantage to get the most magnification to put the image at the near point. The problem is that that actually hurts your eyes after a while. And so for that reason, we're going to opt for comfort, and we're going to attack everything as if we create a smaller angular image, but at a comfortable viewing distance instead of, you know, take that book, hold it close to your eyes, see how it feels to read at your near point. It's not very pleasant. Okay, so here we have our object and we have an image, okay? And then just as a reference, if we have an object at the near point of our eye, this is the biggest that we can make it unaided. And so magnifying lenses magnify, and when we talk about magnification, what we want to talk about is not the size of the object to the image. That's actually not what we're interested in. In this case, we want to know how much bigger of an angle can we make it than our eye can make unaided. And so it's the size of the image from the lens divided by the size of the object with the unaided eye. That's actually what's relevant for us. And so we're going to compare theta 2 and theta 1. Okay, and so if I look at the tangents of both those angles, okay, so theta is roughly equal to tan of theta for small theta, and look, in optics you make a million approximations, so if you don't buy this, you need to go, I don't know, study something else. But anyway, this is the height of the image over the distance of the image, the height of the object over the distance of the object, algebra. We apply the thin lens formula. You can pause the video here if you want. I just don't want to spend a lot of time on it. I want to keep cooking. Eventually, what you end up with is a magnification formula that depends on where the image is located. And so you might say, well, I don't know where the image is located. Well, one thing you can do is you can move the object around until you get the image where you want it. Where you want it? Well, there's two places to look. One thing is move the object around until it's at the near point. There's some special place where you'll get it, and then that is actually the maximum magnification. The problem is it really hurts your eyes to do that. You get a headache after a while. And so typically what we'll opt for in this video is what's called relaxed viewing. And so in that case, you actually want the image to appear infinitely far away. And if you remember, the best place to put it in that case is at the focal point. So you position the magnifying lens so that your object is at the focal point, and you get a bigger image at a relaxed distance. It's not the biggest that you could make the angular image, but it's comfortable, okay? So that's the idea behind a magnifying glass. What happens if you want to make even more magnification than this? This you get a magnification of, like, I don't know, 5 or 6. What if you want 5 or 600? Okay, fine. Use 2 magnifying lenses. Now I have 2 lenses. Each of these lenses has focal points. I can make an object. My object comes in. It makes a real image on the other side of that first lens because it's outside the focal length. That real image turns into an object for the second lens. In other words, I'm going to pretend that that is not an image. It's an object as far as the second lens is concerned. And look what it does. This object is located inside the focal length. And so it does what objects inside the focal length do, which is to say it makes a divergent image, and eventually it'll form some virtual image that is located farther away. This guy is, after all, it's just a magnifying glass. That's all it is. I've put 2 lenses in a row. The second one's a magnifying glass. If I put it right at the focal point, there's my relaxed viewing that I was talking about before. Okay, what does the math look like? So if we look at the magnification from the first lens, this is just straight up normal magnification from a lens. This is the hard work that we did last time. We combine these 2 things together because if we magnify a magnification, you end up multiplying them together. So I do a little bit of algebra. I'll let you look at that on your own. The result of all that algebra is that when I slam all this stuff together into one piece, I end up with the magnification formula for a microscope. So a couple things to keep in mind. This is the magnification due to what's called the objective lens. This is the magnification due to the eyepiece. This 25 is there because of that near point. Remember, we're comparing to the near point the whole time. Okay, and so this is our formula for relaxed viewing. So it's the product of these two focal lengths at the bottom. One thing I'll point out that is a source of confusion. Sometimes people think L is the distance between the lenses. It's not. It's actually the distance between the focal points of the lenses. And on most microscopes, like the manufacturer will just make that 16 centimeters or something like that. Some non-ridiculous number. Okay, so this is a microscope. This is how a microscope works. You can get magnifications of, I don't know, a couple hundred with a microscope. Now, this is good because you can put the lens very close to the object you're looking at, and this takes a small object and turns it into a big object. What happens when you're using a telescope? When you have a telescope, it's actually a little bit different. So in this case, the light comes from very far away. You don't have any choice about where you're going to put it. You can't say, oh, I'll put the object here to make the image in a certain place. The image from an object that's infinitely far away forms at the focal point. You don't have a choice. So whatever lens you put first, you're guaranteed to get an image that forms at the focal point of that first lens. That's a problem because if that focal length is pretty far away from the second lens, then you're going to end up forming a real image on the other side. That's a problem unless that happens to be where your retina is. And generally, we don't know exactly where that's going to form. And you don't want to be like, oh, I need to back away from the telescope. So the solution here, since you can't move the object, is you move the lenses. You rig it so that the focal length of the first one creates an image at the focal length of the other one. In other words, just rig it so that the lenses, the distance they are apart is the sum of their focal lengths. If you do that, you end up with some huge image at a relaxed distance far away. To be clear, this isn't a new analysis. I still have some magnification from the first lens, which acts like a real lens, and then I have the eyepiece, which acts as a magnifying lens again. Okay, so here I'm just looking at the angular magnification in both cases. I'm doing that tan theta roughly equal to theta thing again. And then if I follow through, the magnifications are the product of the two angular magnifications, and you end up with something that looks like this. The idea is the same. We are still using magnifying lenses and regular lenses. Okay, so like the big idea is, what can you do with a couple of magnifying lenses? And the answer is this. One thing to keep in mind is if you've ever seen those pictures of like, I don't know, Galileo, or I don't know, probably not Galileo, but these ancient astronomers, and oh my gosh, holy Toledo, they're looking through telescopes that look like this. Why are they looking through telescopes that look like this? Well, if you look at this formula, you can see that the bigger you make the objective lens, the more magnification you get. And so if the objective lens has a huge focal length, you need the focal length of the eyepiece to be where the image is formed, and you want to make that as small as possible. So in order to do that, you need a very large tube. If you want something funny, Google image of world's largest refracting telescope. It's enormous. The tube is, I don't know, 30 feet long or something, and the astronomer looks like a little person underneath it. Okay, so here's a quick summary. You have, this is the magnification for relaxed viewing, magnification at the near point, which I don't recommend doing for a long time. And then you've got your microscope and your telescope. Typically, you talk about tube length in the telescope, which literally is the distance between the lenses, and then it's the sum of the focal lengths. And then L, this is the parameter in a microscope, is the distance between the focal lengths, not the distance between the lenses. Okay, hopefully this was more helpful than confusing.